All right, so I sent you an email, and I told you to look here for the two keys. So you either have October in the heading, Oct in the heading, or October. So let's go to the document camera and just take a quick look. People did really, really well on this exam, by the way. So this is the Oct version right now, and people did well. I'm not going to go over the individual, over all the problems. I just want to look at one where lots of people got it wrong. So it's on the last page. So many people got it wrong that I think it's worth going over. So on page 6, question 8, the answer was 420. And on the October version, the answer is 380. So people made a very similar mistake here. Most people knew that, okay, you have 30 numbers, and this is where people messed up. 30 numbers, they have 10 numbers each. So people forgot to multiply by 10 here. Here you had averages of 2, 3, and -5 for the groups. And here you have 1, 4, and -5. So people multiplied by 3 here just because I think you were just on automatic pilot thinking that was like the examples in the homework. You had 3 numbers for each group. But you understand there's 30 numbers. So for each one of those 30 numbers, they're getting their prediction is the group average. So there should be 10 here. Very few people got that right. If you did, you should feel really proud. Other than that, the errors were just pretty much scattered. Most people got the rest of it correct, so I don't need to go over it unless you have a question, unless somebody wants me to go over some particular problem, but the answers are online. And just make sure your own answers, that your numbers add up. And I'll let you out a little bit early if you have questions. So you can talk to me about your own exam if you don't understand anything. How's that? Sound good? All right, so let's just go straight to the lecture. And today we're at the start of this exam 3 material. This is the start of exam 3 material. So this is page 157. Page 157. Okay, so we're finally going to look at what happens when our assumptions for fitting a linear model are violated. So here's our 4 assumptions on this page: linearity, independence of the errors, equivariance of the errors, and normality of the errors. And to check the assumptions, you can look at either the scatter plot or the residual plot. But it's usually easier to spot assumption violations by looking at the residual plots. And when you're in multiple regression, of course, in more than 3 dimensions, we can't even look at the scatter plot at the more than 3 dimensions. So you look at the residual plots. All right, so first of all, linearity. But let's just look in 2D so we can draw it. So the ideal your ideal plot, let's just look in the positive quadrant here to make it simple. The ideal plot should just be basically an elliptical cloud here. Right? And then we fit some regression line to it, and it looks like that. All right? But what happens, lots of times there's curvilinear or nonlinear plots, right? And for example, 2 very common ones would be something where that happens in biology all the time is a J-shaped plot where you might have something like X could be a drug dosage. The more, so, and this is a measurement of, let's say, death rate. So if you don't take the drug, you're going to have a high death rate. Then you take the drug and the death rate goes down. But then if it's you can overdose on the drug, particularly if it's a chemotherapy or something, and then the death rate goes up again. So you get something like that, and you can't, if you fit a linear model to that, what would it look like? Well, it would be a straight line like that, and clearly that's not good because you'd be what? Overestimating in the middle and underestimating on the ends. So this is your y variable, so that's no good. And then, another common plot, I thought we might get it with our data when we looked at money on the x versus some measure of like happiness or something on the y. We did this in our class. We didn't get this, but often you'll get something sort of the opposite. Like if you're very poor, it's probably because people are just in the middle in this class pretty much. But if you're very poor, of course, an increase in money, if you're starving, is going to cause a dramatic increase in X, will cause a dramatic increase in Y. It's going to follow sort of like this. And for a while, it keeps increasing, but then it saturates. Because after a certain point, having more money, even though people think it makes you happier, it doesn't. I mean, what measures of happiness? Objective measurements of happiness, but I'm also talking about stress levels and all sorts of physical measurements that go along with feeling happy, also sort of level out. So, and then again, of course, fitting a linear model to that is a misrepresentation. We want to fit a curve to it. So there's two things you could do. You could either look for, fit a curve, but if you want to do these tests that we've been doing, what you do and what we're going to look at is transformation of the variables. But before we do that, sometimes it's hard to spot this. It's subtle, like on the homework that you're going to be doing that I just posted. It's really subtle sometimes to spot this. You can spot it easier, a violation of linearity, if you look at the residual plots. So what do I mean by residual plots? Here's your scatter plots. So the residual plots, the error plots are basically are just graphing the distance the actual points are from their predictions. And you remember so on the y-axis, you'd have the residuals. This pen isn't working very well. I'm going to see if I have another one that works better. Maybe this works better. The average of all the errors is 0, right? And then we can actually more easily see violations of all the assumptions. So for example, let's say you have this plot, right, this point right here. So that has you're just plotting that distance above. That looks like a high point, it would be up here. And you do that for all of them. And you can just see more easily, especially if there's subtle variations, differences, by straightening that out. That's all we're doing. It's easier to spot violations. So a point that's right on the line is still right on the line, and then you can look at things more easily. With these extreme cases, you don't really need to plot the residuals. So what are we doing? We're plotting, this is x, this is still the x. But on this axis is how far off the predictions are. Sometimes you'll see it as y on this axis too. But we'll do x and just straighten out, make that horizontal. So that's all we're doing. And so you can probably see how these are going to look. They're all, the average of the residuals is 0, right? And so this one's going to look something, this has a little bit above here, it will look like that. And this one will look like that. That's just a rough sketch of it. Okay? Any questions on that? So we'll just do the same with the others. All right, so independence. So the errors in the true underlying regression model must be mutually independent. Basically, what this is saying is that can we model our data as random draws from either a wider population or as random assignment to some condition, to an experimental condition. That's what we're talking about here. Now, the scatter plot should show, and residual plot should show no grouping. It's kind of hard to see independence, lack of independence, I think, in these plots. If I can think of really beautiful examples, I'll come back and do this later, but I was thinking this morning, I think that all the examples I could think of already violated linearity. So I couldn't think of any other good examples. And mostly what you want to do is just make sure that you have an underlying, your situation, whatever you're analyzing, really can be modeled as random draws from a larger population, or like we did with the re-randomization test. Just try to model it somehow as random draws from a random division of the population or from a wider population. But if you can't really do that, then you're going to have a violation of independence, which is probably one of the most serious violations. Okay, so I'll get back to you on that if I can think of a good way to look at it visually. All right, now, so the next one is equal variance. And we've talked about that a lot, that the variability of the y should be the same across all values of x. That's called homoscedasticity. Homo meaning same, like in homosexual, and skedasticity meaning spread. Skedasticity. Skedasticity. All right, so we want equal spread. So a classic type of plot you'll see that comes up a lot, and this is not looking good. I don't know why that is not looking good. Maybe if we do this. It should, come on. You're supposed to, it's not focusing. Sorry to waste your time here. It's so slow in focusing. Okay. All right, maybe that will help. All right, so now we're on this equal variance one. So what I said is here, a violation, a bad. This would be bad. These are bad, by the way. This one is bad here, and this one's bad. Ideally, it should look like that, okay? And here's a violation of linearity. You could still have linearity, but it could look bad like this. Like, here's another bad way. Now, you're going to have linearity, but it's going to be not equal variance would look like what? You'd have something, here's your linear, but you have very small errors here, and then maybe as x gets bigger, your variance around this regression line gets bigger. So it's like a fan. So when you get way out here, you have lots of spread, but maybe down here you don't. Something like that. That's a fan shape. That's bad. You have y and you have x. Okay? And fan-shaped is a very common way for it to be bad. And the residual plot, of course, would just, this is an extreme example, so the residual plot would look pretty much the same. Here would be your residual plot. It's centered right here, all your errors, and you just have little errors here, and then they just go out. And, so you don't have equal variance across all values of x. And so we'll see that a good fix for this often is to take the square root of do a square root transformation. And then we're going to look at that later in the hour. And then the normality, violation of normality. What does normality even mean? The errors around the regression line at each value of x are approximately normally distributed. And then you should look not so much at a residual plot, but a histogram of the errors. And they should look approximately normal. So ideally what you want, the ideal, it's kind of hard to draw, but here's, let's say, y and x, and let's say you have some pretty scatter plot, like we've been drawing. What you want is within any vertical strip, I'll make an exaggerated vertical strip like this one or that one, so at any value of the x's, if you want these errors inside here to be normally distributed. That means that a lot of them are close to 0. 2/3 of them are going to be within 1 standard deviation of the errors. And then not very many are going to be out here. So you can imagine like little normal curves within every vertical strip centered at its prediction. So if you drew a residual plot of it, what would it look like? Now it's not a residual plot. Let's draw a histogram of the errors. That's what we want to do. So we'll draw a histogram of the errors. And most errors will be around their predictions. They'll have very small, most of the y values, the predicted y's will be, and the actual y's will be pretty close to each other, right? And then as you get further, there's going to be fewer and fewer of them further away. So it will look like a normal curve centered at 0, you know. You know, 2/3 of the residuals will be within 1 standard deviation of the errors away from their prediction. And, 95% will be within 2 standard deviation of the errors away. And 97% will be within 3, etc. It will follow a normal curve, roughly. That's ideal. And then we can use our F statistic, our T statistic, and all that very easily. Especially with small samples, this is important. Yeah?
If you want equal variance
Mm-hmm.
in your regression, why do you want an elliptical shape scatter plot?
Oh, instead of, good question. You mean like, I know what you mean. So you mean like, why wouldn't you, if you want, his question was, hey, if you want equal variance, why do you want something like an elliptical shape with points at the end? Is that what you mean? Yeah. Instead of like why is this ideal? Instead of probably what you think would be ideal would be something like that, right? Yeah. Like it's equal all the way across. Yeah, that's a good question. Does everybody understand that question? Anybody else want to answer it? Okay, so why doesn't it look like this? Isn't this equal variance? It really should look like this if there were points, if there were a whole lot of points over there. It's just that generally speaking, at the ends here, this is x and this is y, there just aren't that many points here. You know what I'm saying? So, and since there aren't that many points, the points that are there are more likely to be close. Remember, if you have a normal curve and you just have a few points, it's unlikely they're going to be way out here. So the idealized version of it would just be in the average, you just have a few points there. Not that the variations anymore, it's just you have fewer points at the extreme. That's all it means. That's generally why it looks that way. Good question. Okay, so now, so what's a bad? This is the ideal. What's bad? This is so hard to see. Also this is, this is the one that's you're most able to violate with a large sample because of the central limit theorem. It's just not that serious to violate this with large samples. It's more important in small samples. So what does a bad one look like here? So Oh, so sorry, guys. Technical difficulties today. There you go. Okay, so, all right, so bad plot would look like what? So, in this elliptical shape here, what we would have, we could still have this elliptical shape, but within each like little strip, let's just do the same thing. Within a strip, you might have something really bizarre like, okay, like most of your errors, you don't have a normal curve in here. It means like you're going to have a lot of errors way out here and just a few in there. So you might have something strange like that, where we have a few errors in here, a lot of them are out here. You still sort of have the outline of the elliptical, but within the strips, they might not be normally distributed at all. They could have any kind of distribution. I'm doing a weird distribution of, let's say if I plotted the errors, they might look, I don't know, this is sort of like within some strips, they might look like this. Like around 0, they might be symmetrical, but be like this. That's what I drew here, like a lot more errors out here. In some strips, and then in other strips, you might have different, you won't have normal distributions through all the strips. You just have weird different things. Okay? So let's move on. And so what happens? So what do you do if you have violations of these? So that's on the next page. So if the scatter plot follows a nonlinear pattern, then we can try following these steps to make the plot look more linear and to make the errors around the regression line normal. And you can follow, this is just trying to put into a systematic way to do it. It's not necessarily the only way to do this. So, so let's say you want to make the plot more linear. You want it to look, you would look at the histograms of the individual variables. So you might as well start with your y variable. And if it's symmetrical, then leave it as it is. Actually, if it's symmetrical and normal, and roughly normal, so if the y variable has a nice distribution like this, then leave it like it is. Maybe look at some of the x variables. But if the y variable is right skewed, so if it looks, and let's just talk about positive y variables for now. So if it's right skewed, that means that what? That means that the bulk of the data is down here, but then there's these extreme values that go way out here. That's called right skewed. What you want to do is bring these values in more. So these transformations would do that. For example, a log transformation, or imagine changing it to exponents. So if this is 0, 0, 10, 100, and then 1,000, et cetera, et cetera, et cetera. If you, and you get up to 10 to the 6, well, 10 to the 6 is going to go to 6. 10 to the 5th will go to, so we'll bring it in a huge amount. It will have a big effect on these extreme values, right? This is a little bit dangerous just because it's going to reverse the direction. The bigger the y, the smaller the value, so it will flip it too. That's not done as much, but these two are done all the time, and so we'll look at some examples of those we can do right now. Why don't we look at an example, just so you get an idea of what I mean. So let's go to our data program. Whoops. And to our survey data. So we'll go to all right, so your income. The question that asked, not income, but money. Money is always right skewed. Where is that? How much do you expect to earn? 20 years down the road, how much money do you expect to make per year? So answer in thousands. You understand why it's going to be right skewed, right? So let's look at the histogram of it and see what we can do to make it look better. So if we go to the histogram of your answers, you see what happens? In order for the graph to include this is in thousands, these huge answers, if they space everything evenly, all we see is, you just can't see anything. You just can't see it. So we could try a square root, just so we can see the data, and then we could try a log, and then you can see, once it's in exponents, you can see it a lot better. Now, by the way, this is not log base 10. This is written that way, but it's a natural log. So it's log base E in the data program. It just was written log, but it's all natural log. So that's what we're doing here. So you can see how, now we can see, otherwise you can't even see it. So that's a case of, and this happens all the time with lots of things in nature on a log scale. So you have to log it before you can even see it or make a model. Okay, so let's go back to the data again. So now if it's left skewed, and that left skewed is actually like our exam scores. I'm asking you on this survey that was supposed to be due tomorrow, but I can extend it till Sunday because I haven't put it up yet. I'll extend it till Sunday. I'm asking you what your exam scores are, partially so I can get some data that's left skewed and plot it, because that looks like most of you did really well. Half the average was an 86.5, but then there are some really low scores, unfortunately, that go way down here. So I want to show you transformations with our exam data, so I'm asking you for that on the exam. And then what do? Then what we want to do is square the values to spread. And I shouldn't put it this way, it's not like negative scores. I'm sorry, we're all in the positive realm here. That's pretty dumb. All right, so we're still that's still 0. So if we square the people who did very well in the 90s and 100, we're going to spread this out more, and it will be more normal. It'll spread it out so that we can have a normal. Like right now, what's happening is there's no discrimination between these people up at the top. It's really hard to see them. They're all bunched up, especially between 95 and 92, 93, 94, 95. Around, they're just all squished. So if I wanted discrimination for some reason, I'd have to spread them out at the top. Or else give a much harder exam. Right? That's why people do, to get some discrimination, because you guys are doing too well. I love it. You're learning it. It's still still a basic intro class, and I'm just delighted with the scores. I'm shocked by them, actually, but really happy about them. Okay, so now so what are we doing here? All right, so we look at the scatter plot with the transformed y, and we'll do this in an example in a minute. You'll see what I mean, and see if it's linear. If it is, great. If it's not, then try transforming the x variables as well and do the same thing. And then if the data is straight enough, you fit a regression, and you find the residuals and the predicted values, and then you do exactly what we said on the previous page. And we'll do that with an example. We'll look at the residual plots, and you'll have a better feel for what we're doing. All right, so this is as on previous page. So that's a good plan of action. Sometimes none of this works, and you have to say, hey, we don't have a linear model. We're going to have to fit a curve to this. We're going to have to do something else. This isn't what's good. All right, so let's look at an example here that's a very non-linear model. So below is a scatter plot of the brain weight in grams and the body weight in kilograms of 34 species of land animals, 24 species of mammals, and 10 species of dinosaurs. So you get this, here, I'll show them to you. Let's look for them. And let's find this on our data set. Oh, I think it's here. No, I think it's maybe here. Okay. All right, here it is. So now what we want to do, we want to make a scatter plot with, we're trying to predict these animals' brains from their body weight. And so look at this, we make a regression, and we have this slightly negative correlation. Now I was going to have you guess who these animals, like which ones were humans, and which ones were, who the animals were, but I didn't bring my on a PowerPoint, as a PowerPoint is an iClicker question, but I'm sorry, I forgot, I didn't bring my questions with me, so. All right, so I'll just show you, but do you want to guess, who do you think that animal is? We'll see, it's an African elephant. So it has a huge brain and a relatively small body weight. And this is Brachiosaurus. So these are different animals. I just didn't know some of their names. These are all dinosaurs down here. And this is an Asian elephant. And there's a human. And there's a giraffe. Okay, but we can't see. We can't see these. These little animals here? There's a gorilla, a horse. They're just like, you can't see them. You can't even see them. Just like we couldn't see. They're all squished together. So here, let's just start over here. So these animals here won't show up, just like the people didn't show up, except who the bulk of the people in your income data or your expected income data. So what can we do? So we can do a transformation. And what we might want to do is a transformation, let's try of the y variable, and let's see what happens when we do. Here's our regression line. So let's transform it to a square root. And that's, I think, what I have in your notebook, don't I? Oh, no, I don't. I go to the histogram. Sorry to jump ahead, guys. Okay, so let's go to the histograms, and let's take a histogram of the brain weight. And you see how it's very right skewed here. The bulk of the data is in here, and it's very right skewed. So if we try a square root, that helps a little bit. And let's try, if I make it, I don't know how many intervals I should have. Let's try a log. And that makes it better. It's not perfect. You see how the shape of these distributions changes depending on how many bins you have? I made it look pretty in your notebook. I chose 7 bins, I think. And it looked pretty, but it's better. Okay? So it's better. And then, so let's go back to the notebook. All right? So that's where we're at here. And I say, notice how once you make the scale big enough to see the big animals, most of the points are scrunched in near 0 for both weights, body and brain. And you just can't see them. And you see, neither can the fitting program. This is a fitting program. It can't see them either. So it just can't distinguish between them. And it pays little attention to these small numbers. It's completely dominated by the big numbers. Yet that's where most of the animals are. And you want a transform that counts these little animals just as much as the big ones. And when I always think when I do this of my favorite children's book, Horton Hears a Who. And it says it's about an elephant, Horton, and he's trying to save these who's down in Whoville, and they're very little, they're tiny, and people are going to they're going to get destroyed. So he says a person's a person, no matter how small. So that's the idea of it. And I feel like on this planet, the planet's getting destroyed because all of us people, little people, they can't hear our voices, and we got these big, you know what I'm talking about, corporations that are dominating everything. They're the, you know, we can't even see the animals that matter, right? So I always think of that. And so I think about, it depends what you want to do, but if you want to count those, you have to do some kind of transformation. Otherwise, you can't see them all. Because when you have such a right-skewed data, all that shows up, unless we visualize things differently, are these giant, giant numbers. Okay? So that's the idea. And so we do the transformation here. And first of all, is the plot linear? No. It's right-skewed. How are you going to remember that? Well, remember that there's extreme values away from the data are to the right of the main data. Where most of the data is, these are far to the right. So it's called right-skewed. And right-skewed. And to make it more symmetrical, what do you want to do? You first try the square root, because that's not as dramatic a transformation. And that's what we did. And it didn't work as well. And here, we can try the log. And this is log base E, usually. Even though it's written log in our, it's written like this, without, you don't see the little e in our data program. So that's what we want, not base 10. We could have done base 10, but most people operate in base E. Okay, and if it was left skewed, what would you try? Well, then you'd want to do the opposite. You'd want to make those bigger values, you can't see them. Like in this class, I can't really distinguish between the really good students, and that's what's happening in a lot of our classes. You can't, you're all bunched together at the top, you all get A's, right? So now you have to get recommendations and do all this stuff to distinguish yourself, because people looking at your transcript can't tell the A's apart. They're all squinched together. And it doesn't make sense to do one of these transforms, really, I mean, they don't do that, so they have to do other sources of people, like graduate school programs and so forth, don't count the grades as much. I mean, you have to have A's, everybody has to, but the A's are, almost half the class has A's, right? It's astounding. So they're all squished together. If we had a better measurement of grades, we wouldn't have to have all of you scrambling to ask people you hardly know for recommendations. You know, that's what's happening to all of you, because the grades don't mean anything. In my day, the grades meant something. C was the middle. That was the middle grade. So if you got an A, you were pretty much in everywhere, because that was very unusual. Like if you had a high average, like an A average. You know, in math classes, there was just a few people who got straight A's. Less than 10% for sure. So, I mean, there was like A's and F's were pretty much the same. It was a distribution like that, so you didn't have to go, you just worked really hard in your classes, and that was all you had to do. You didn't have to, like, I don't know. But for now, somehow there's just been this insane grade inflation, so you work really, I just don't get it. But now, so that's what's happening. There's no discrimination at the top. That's fine for gen eds, but by the time you get to higher level classes, they should have more discrimination. Anyways, so that's the idea. So if they're less skewed, the transformations that we would do would square them or cube them if they're positive. That's, you can't do that if they're negative. Or E, okay, to the Y. And that's very rarely used. Mostly look at squares. All right, so now, here's where sorry I skipped to this. I said, look at this. I jumped ahead before to this page, and I said, look at the scatter plot with the transformed y's and see if it's linear. If not, try doing the same transformation on the x variable. So is it linear yet? No, it's not linear yet. So now we're going to go, let's look at it. Now we'll transform it, and we'll get this. So we can just jump to that, and I can show you. So we'll go to the, here. And so we can go to the scatter plot. And you should play around with this data too. And it's kind of fun playing around on this data program. So what are we doing? Body weight predicting brain weight, and then we first transformed the y's, and we did first it looked like this, then we did that, and now we could see these animals a little better. We can at least see who they are, right? A little better. But now when we do the log of y, we see there's a mouse, a hamster, here's the rodents. Etc. And then but still, it doesn't look great, we have to try the x too. That doesn't look so good, and this looks by far the best. So now we have this nice linear plot that is in your notebook. After taking logs of both weights, we get a plot where all the animals show up, and the fitting routine sees all of these points equally. So now we see this is the mouse, there's the cat, these are probably the elephants, there's the human, and this group down here is probably the dinosaurs. Who's that? Dinosaur, that's a Tyrannosaurus rex. That was a smart dinosaur, I guess, because he's not a vegetarian. Some of these didn't have to be as bright. Okay, so this is what it looks like, and who's this? Oh, the mouse. I have a mouse at my house right now. I've been catching it with a humane trap. I caught one of them, but now the next few, I don't know if it's one, he keeps escaping. He just takes all the food and just leaves. It's like the Houdini mouse. And so I don't know what to do. I have to go back and get another trap, those humane traps. But it's amazing because I hear him in there, and the next thing I look, I try to get him, and he's gone. He just comes right in and comes out. So I don't know how I can do it. I looked at the trap. It doesn't look like I don't know what he's doing. And I don't know if it's one or multiple ones or whatever. But I've been feeding him so well, I'm hoping he's going to get so fat he'll get in and he won't be able to get out. So but I didn't realize how below the line they are. Anyways, so that's what it looks like. And if you wanted to show the errors, you can see what that is. There's the error plots. And that's what that looks like. And the error plots show a pattern. Look at that. So this is not ideal. See, they show this pattern. But we're going to stop here and do this example, and we'll clean this up later. You see, this is still not ideal. Because look, you saw those error plots still showed a pattern. But it's better. All right, so any questions so far? Okay, and look at this. Look at this equation now. Now we have equation in logs down here. So it's saying log, and this log is always natural log. So this is really ln. All of them are in this data program. Okay, so we have an equation in terms of logs, and look at the r, it just skyrocketed. Now we have a very nice, strong, linear relationship. It doesn't do so great for these group of dinosaurs. It doesn't do terrific for the human. Has a big residual. It does great for the cat, we just saw. It's a very good prediction for the cat. It follows this pattern, but we're going to stop it, here and do some estimates, and then next class we'll make it even look better. Okay? We'll break up the data and make it look better. All right, so now here's what the rest of the hour we're just going to be making these predictions for log transformation. So what's the idea here? We've got this equation in terms of logs, and it's linear, right? But we're really not very much interested in the log. I mean, we might be, but then we want to transform back to the actual brain weight, not the log of the brain weight. And so we're going to look at how we do that, and how we build confidence intervals around the transform variables first, and then use those to get confidence intervals around our original variables. So it's just interpreting log equations here. That's all we're doing. And you have homework on that too, and then we're going to just do these 2 pages, which is very similar to the homework, and then I'm going to try to let you out a little bit early. So let's try. Okay, so here's this equation we just saw on the previous page. That's what we had on the previous page, and we also got the standard deviation of the errors here. Okay, so it's the log of the brain weight is equal to 3 plus 0.32 times the log of the body weight. So we want to use the equation to find the brain weight of a cat given the predicted brain weight of a cat given that the cat has a weight of 3.3 kilograms. So we're just going to use that. So we'll just do it, and we'll say the log of the brain weight of the cat is just equal to 3 plus 0.32 times the log of the body weight, and we'll just put that right in here. And I did that, and I got 3.382. Now that's just an exponent. It's a log, so it doesn't have any units on it. Now I want to get the actual brain weight, so I just have to exponentiate both sides. So anti-log the brain weight, which will be, and I got 29.43. Now this has the grams attached to it. That's an actual weight. All right, so now it says the actual brain weight of the cat is 25.6. What's the residual? So the residual is just the prediction error. It's just the actual minus the predicted. So that's 25.6 minus 29.43 grams, and you get it's negative 3.83 grams. Okay, so it's just this distance. The cat is just a tiny bit below the prediction, just a tiny bit below. Now we can do the same thing with the human. Use the equation to find the brain weight of a human who is, okay, so we'll just do the same thing. So now we're going to take the log of the brain weight for human, and that's 3 plus 0.32 times the log of what? 62 now. And I did that, and I got 4.32. And so now to get the actual brain weight, I just have to, anti-log both sides. So I get brain weight is equal to e to the 4.32, which is 75.24 grams. Now the actual human's weight is huge, much, much bigger than that. So the residual is going to be what? The actual minus that predicted, which is 1247.76 grams. And that's much bigger, and that's why we have this big residual for the human. Okay, now let's see what's the next thing. Any questions so far? Yes.
So like it originally said that the cat's weight is 3.3 kilograms. Why did you plug in 33?
Because that was an error. That's a giant cat. That's like a bobcat. A tiger. I love cats. That's why I have mice. I don't have my cats anymore. Got to get more cat. I got to get a cat. Okay, so now we're going to change. Thank you very much for catching that. Okay, log of the brain weight is, okay, so this we want to change back, right? So how do we change this back? I just want to show you what happens here. Okay, so note when we have these log equations, we want to change it back to, it's more intuitive to just go to change it back to our original variables, because most people don't think intuitively in terms of logs. So to change it back, look what happens. These, the intercept and the slope, are betas that we're estimating is here in the linear equation, are the exponents right there in the, when we transform it back to our original brain weight equals the intercept times, it becomes the body weight. So that's the form, and you can see why that would be so. We have the log of the brain weight, you can just do it, equals 3 plus 0.32 times the log of the body weight. So what I'm saying is that these right here are going to become exponents. That will be the exponent the body weight will be raised to, and this will be part of, this is just the will be part of the coefficient in front of that. So we can do that. So we're just going to exponentiate both sides, anti-log them, so we get the brain weight equals E. I could raise that whole thing, but here, you know that when that's going to become multiplication times E, right? When I raise it up to, it's just, so it's going to look like that, raised to that. And then this is commutative. So I can just, I'm just going to rearrange the order so you'll see what I'm doing better. So I'm going to put log of body weight first times 0.32. Now that's the same thing, right? So this part right here is just body weight, right? Because E raised to the the log of the body weight is just going to be the body weight. So we get here, so this gives us, this will give us E, this whole part is body weight, and now it's, that is raised to the 0.32. I didn't bring my highlighter, so I wanted to highlight this, but this is, there's that is the same as, there's our exponents, just like what we did. So, any questions? This is, all right. Now, I mean, I know that most of you, this is like arithmetic to you. You're so used to it because you're math majors, but there are people in here who probably haven't had algebra 2 haven't worked with logarithms for like 3 or 4 years, and they might be rusty. So don't hesitate to ask for help, come to office hours or whatever you need to. And don't feel bad about yourself for that. That's just, you're not used to, if you don't use math, you forget it. So if you're in that situation, it's no problem. You'll catch up right away. Just, you might need some help or review. Just do the homework and see how you do. Okay, what if we had taken log base 10 instead of log base E? What we would have got, would we have gotten the same equation? If not, what would change? Well, the only thing that would change would be the intercept. Only the intercept would change. You know, I'm going to, since this isn't on the homework or anything, I'm going to wait till next time because I want to let you, only the intercept would change. I want to let you out early so you can talk about your own exams. I want to get to the next page. And this isn't, you don't need this right now, but it's not going to change. All right, so now let's just go to the confidence intervals. And so we can get out of here more quickly, right? Okay. So now let's compute confidence intervals for the 4 transform variables. Now we have to assume all those assumptions are met, and they aren't quite, but I just want to give you the mechanics of how to do it. So this is assuming we have those 4 assumptions met. The normality wasn't quite, remember we're not quite there yet. We have to examine residual plots, but this is a good place for you to learn how to do the mechanics of doing the confidence intervals. So let's assume that the 4 assumptions were met. Assuming 4 assumptions are met. And we've already looked at the residual plots. and change things to make them look perfect. Okay, so now, all right, we transform the variables in order to get errors around the regression line to be about normal. This means we can use this SD errors. Remember that SD errors, like right down here, we've got this equation, and we've got this SD errors. So we can build confidence intervals with them. But this is for the log, right? So this SD errors is associated with the log. So if we build confidence intervals, like we usually do with a 68% confidence interval being our estimate, our prediction plus we're putting error bars around it. So it's our prediction is a log, the log prediction, plus or minus like one standard deviation. It's going to follow the normal curve of the errors if they, right? And that's why we have to check that normality assumption. All right. And between 68% of the errors are going to be within one standard deviation of the errors of the prediction. So this is for logs, because we did the whole thing with logs. And then 95 will be within approximately 2. So we have -2 and 2. This is what we're doing. So we can use this, but we can only use it on the log, not on the brain weight itself, right? So we have to use it on, remember what our prediction was? What was our prediction for the log? It was for the log of the brain weight. We got, what did we get? 3.382. And for the brain weight, we exponentiated that. You know, we put the weight in, that's what we got here, and then we exponentiated it, and we got that. So what I'm saying is, we want to put confidence intervals around our prediction for the cat's weight, but we can't do that. We have to put it around this first. So you just have to do it in 2 steps, because this is associated with that, with the log. So we have to do that one first. All right? So let's do that. So we find the endpoints of the confidence interval for the transform variable. Okay, so let's put confidence intervals here. So what are we going to be doing here? We're basically we're saying, okay, we're going to take this log of the brain weight, which is 3.382, and plus or minus z, the critical value of z associated with 95%, that's about 2, let's just do it in our head, times the standard deviation of these errors, so that's 1.6. So that's what we're doing. So we get these, I'm sorry, this is very hard to see. This is like our 3.382 plus or minus 2, because we're going to take a 95% confidence interval. This is a 95% confidence interval between 2 and -2 standard errors, right? That's where that 2 comes from, times, if I wrote it up here, you could see it better. This is 3.382 plus or minus, there's our, it should be 1.96, but we're just going to approximate it as 2, times 1.6. That's what we're doing. And so the endpoints are what? 3.382 minus 3.2 and 3.382 plus 3.2. So those are our endpoints, and this is nothing new. This is our confidence interval, but this is a confidence interval for the log of the brain weight. So now what do we want to do? Now we just want to exponentiate those. Anti-log both endpoints. So we'll just e to the 0. This will be our lower endpoint for the actual brain weight, not the log. And we'll do the same here, and then we'll be done. And then we get, look at this confidence interval. You're going to be, it's 1.2 to, look, because this is an exponent, this is going to be gigantic, to 722. So that we have these what's called asymmetrical confidence intervals. Our estimate of 29.43 is not in the center of these confidence intervals, right? This is not in the center. The confidence interval is symmetrical for the log our log is in the center of, 3.382 is in the center here, but it's not for the actual weight. The estimate is the geometric mean, not the arithmetic mean. So I'll just write that. So note, we have these asymmetrical confidence intervals. We don't have brain weight, 29.43, plus or minus the same amount. Like it's not in the middle. It's not the arithmetic mean of the two endpoints. Instead, what do we have? We have, our log is in the middle. We have 3.382 plus or minus 3.2, which means that which means what? Which means that 29.43 is not the arithmetic mean, it's the geometric mean, meaning it's the square root of its endpoints, of the square root of the product of its endpoints. See, that's what you have to check. Because why? Because this is really e to the 3.382, right? That's how we got that. We raised e to the, that's how we got that. I should say because. So that is equal to, right, e to that, which is really 3.382 minus 3.2. This is okay if this is, this is just arithmetic. It's nothing special. And you're not going to be asked to do this on the exam or anything. It's not really. 3 to the e to the 3.82 plus 3.2.